Today we are going to learn some rules for differentiation that should make differentiating functions much easier for us. So there are 7 main rules we're going to talk about. So the first rule of differentiation is that the derivative of every constant function is the zero function. So here we're going to write this as df dx is equal to d dx of c, which is equal to 0. So, for example, if I had the function f of x equals 3, I know that the derivative of this function is 0 because 3 is a constant. Our next rule is the first step in differentiating a polynomial. So this is the power rule for positive integer powers of x. This says that if n is a positive integer, then the derivative of the function x to the power of n is equal to n times x to the power of n minus 1. For example, if f of x is equal to x to the 5th power, then d dx of x to the 5th power is going to be equal to 5x to the 4th power, as it is 5th power, so 5 minus 1 gives us 4. Okay, our third rule is called the constant multiple rule. So if u is a differentiable function of x and c is a constant, then d dx of cu is equal to c times du dx. So what exactly does this mean? Well, we can see in our function we have a constant c, and then when we take the derivative, we do the derivative of that function u, and then just multiply it by a constant c. So let's look at an example to help us understand that a little bit better. So if f of x is 7 times x to the 4th, so what we're going to do is we're going to take our constant here, 7, we're going to put on the outside of the derivative of this part of the function right here. So we can say d dx of 7x to the 4th, and yep, we're nesting a whole bunch of parentheses here. This is equal to 7 times the derivative of x to the 4th, which is 4x to the 3rd, or this whole entire thing can be written as 28x to the 3rd. So just looking at this name, the constant multiple rule gives us a clue about the rule. It means that you have a function, usually some form of one of our parent functions, and it's being multiplied by a constant, which is just any number. Okay, so these last 2 rules were helpful for differentiating monomials. To differentiate a polynomial, we'll also need to be able to differentiate sums and differences of monomials. So we have a sum and difference rule. So rule number 4, the sum and difference rule. The sum and difference rule says if u and v are differentiable functions of x, then their sums and differences are differentiable at every point where u and v are differentiable. So at such points, the derivative of u plus or minus v is equal to the derivative of u plus or minus the derivative of v. So you can break a sum or difference into its terms, find the derivative of each by itself, and then put them back together with the operation plus or minus that was in the original function. Using rule 4, we're going to try and do this example. So let's find the derivative dp dt if this function p is equal to t to the 3rd plus 6t squared minus 5 over 3t plus 16. So let's go term by term and apply our other rules as needed. So using our sum and difference rule, we have dp over dt is going to be equal to the derivative d dt of the first term, t to the third, plus d dt of 6t squared plus, minus d dt of 5 over 3t plus d dt of 16. Next, we'll use our power rule and our constant rule as needed, term by term, to differentiate each term as we go. So we can say dp over dt is equal to, so looking at the first term, t to the third, we'll use our power rule. The derivative of that term is 3t squared plus, now here's where we're going to use our constant multiple rule. So we're going to have 6, and then we're going to differentiate t squared. So 6 times 2t to the 1, so just 2t, minus, we've got 5 thirds, and then the t is going to disappear at this point. And then our last term is going to be plus 0 because the derivative of a constant term is 0. And our final form of the derivative is 3t squared plus 12t minus 5 thirds. That is our derivative of that function p. Okay, so next up we're going to talk about products and quotients. So our product rule is here, and it tells us that the product of two differentiable functions is u and v. We need to be careful because the derivative of the product of two functions is not the product of their derivatives. So for example, we know the derivative of x squared. So if we want to find the derivative of x squared, we know dx of x squared. What's that going to be? Well, we know, using our power rule, that it should be 2x. We can think of this as being like the derivative of x times x. And you can see where our product rule is going to come into this. So we have x times x, and the derivative is going to be 2x. So we have to figure out a product rule that works and gives us this same answer. Because if we split it up like some people want to do, looking at this x times x, oh, let's just split it up into two terms like we do with addition. It's not going to work. So that's going to be, if we have, here's our non-example, if we say dx of x times dx of x, well, the derivative of x is 1. The derivative of x is 1. So if we split it up that way and did the derivative of x separate, we would end up getting 1. So these are clearly not the same. So now let's go back up here and look at what the product rule actually tells us. The product rule tells us that if we have two functions, u and v, and we know they're both differentiable, first thing we're going to do is we're going to take this u function and we're going to multiply it by the derivative of v. Then we're going to take v and multiply it by the derivative of u. And we're going to add those two together. Let's look at an example of this rule. We have the function f of x is equal to x squared plus 1 times x cubed plus 3. And we need to find the first derivative of this function. So using the product rule, let's say that function u is the first part, x squared plus 1. And function v is the second part, x cubed plus 3. So using the product rule, we're going to now figure out our first derivative. So if we are finding dx of x squared plus 1 times x cubed plus 3, we know the product rule says take your u function, multiply it by the derivative of your v function, add that to the v function times the derivative of the u function. So what's that going to look like? Well, we said that our first part of our function is u, and our second part is v. So I'm going to label those so it makes it a little bit easier for us on this next step. So we're going to start and say u, so that's x squared plus 1 times the derivative of v. So the derivative of v is going to be 3x squared. Plus, now we switch it around. Now we start with v. Now we have x cubed plus 3 times the derivative of u, which is 2x. Then we can use our algebra skills to simplify by distributing our monomial to our binomial. And our final answer we get is going to be 3x to the fourth plus 3x squared plus 2x to the fourth plus 6x. And then we are going to combine like terms, and we will end up with 5x to the fourth plus 3x squared plus 6x. And this is our final answer. Now, we could have done that example by multiplying out the original expression using the distributive property up here and distributed the terms and then differentiated that polynomial, but that strategy doesn't work on functions like if we had on all functions. So if we had something like x squared times sine x, I can't distribute that and then break it up. So this rule is really important, and this is an easier example to understand than something like x squared sine x. We'll get to one of those later. Okay, rule 6 is the quotient rule. So we're going to be at a point where the function v is not equal to 0, and the quotient y equals u divided by v of two differentiable functions is differentiable, and d dx of u over v is equal to v times du dx minus u times dv dx all divided by v squared. What exactly does that mean? Okay, so let's take a look at our original function. Our original function is u over v. So then we're going to track where each of these parts go. So let's start with u first. So u is our numerator. Then our first term, we have the derivative of that, minus u function unchanged times the derivative of v. So if we're looking at where v goes, v is the denominator. It starts out being left alone, multiplied by the derivative of u. And then subtract from that the function u, left alone, times the derivative of v, all divided by v squared. So we have v in 3 places. The denominator ends up in 3 places, or some form of it, because we have the derivative as one of these. And our numerator does not end up in the denominator. Okay, let's work an example. So let's say we are trying to differentiate the function f of x is equal to x squared minus 1 divided by squared plus 1. So using our quotient rule, we're going to call our numerator u, our denominator v. So the first derivative of x, following our formula up here, is going to be v times the derivative of u, so x squared plus 1, times the derivative of u, which is 2x, minus u, x squared minus 1, times the derivative of v, which is, again, 2x, all divided by v squared, which is x squared plus 1 squared. From here, it's just a matter of using algebra to expand everything and simplify, and we'll end up with 4x, once everything is simplified and canceled out, divided by x squared plus 1 squared. And we can leave this bottom term that way if you want to. So if we were to graph this, we could graph our original function and this one, and then see if we think it looks correct. So our last rule is the power rule for negative integer powers of x. So if n is a negative integer and x is not equal to 0, then the derivative of x to the n is equal to n times x to the n minus 1. This is going to look suspiciously similar to our just regular power rule when it's just positive powers of x.